Hey everyone, thanks for coming today. This is Charles Liu, application engineer at Markforged. Today we will be talking about uh, the role of carbon fiber in 3D printing. So, I think many of you have heard about carbon fiber. Maybe you've used it yourself. I wanted to give a quick agenda here and just show you what we're going to talk about. Feel free to throw into the comments into the question, the QA area or comments, chat, whatever it's called these days. What you're looking to get out of this session. I'll do my best to provide the service for everybody here. I don't want to just go over information that everybody already knows. So the agenda for today, I'm going to first ask you a few questions. Flip this on you here. Then we'll go through the basics of carbon fiber and talk a little bit about the physics of carbon fiber and 3D printing, and finally go through a comparison of short and continuous fibers. I think the first couple sections will be pretty quick, probably the first 10, 15 minutes, and then we'll spend the bulk of the time on short versus continuous fibers. Will this be available as a recording later? Sure will. So let's go into a few questions. So these questions are for you to ponder. Write them down if you'd like. For me, it personally helps to write things down so that I get a sense of what actions I need to take after a meeting like this. There's a lot of information. So write it down if you'd like. Type your answer into the chat if you're comfortable, or just make a mental note, whatever works for you. But I suggest writing it down. So what are you hoping to get out of this webinar today? There's, the topic is about dispelling the myth of carbon fiber. And is that something that you're actually interested in? Or do you have specific questions? Feel free. This is a forum for you to come and ask those questions. So I would encourage you to be open and ask us what you want to hear. So take a minute to think about what you're hoping to get out of this today. Cool. And I'm seeing a number of questions come in. Thank you, everyone who sent questions. I will take a halftime Q&A answer session. So hold on just for another 10, 15 minutes, and we'll get right to it. So the next question, have you 3D printed carbon fiber before? How many of you are currently customers? If you are a current customer, thank you for joining. It's super exciting to see. And if you're not, have you 3D printed carbon fiber before on another machine, perhaps? And the follow-on question to that, if you have, what did you print? We see a lot of use cases now for functional prototyping. If you're considering a material and you said, oh, it's just not quite strong enough, you might think, oh, well, let me just add some carbon fiber to it. And chances are it will make it stiffer a little bit. It'll make it more stable, more rigid. But I also wonder then, did it live up to the hype? Did for us too, I want to be candid here that Markforged is not a fix-all solution for functional parts. We can make parts well designed in a way that is close to the strength of aluminum, but in some cases you're still going to see that fall in a spectrum between a carbon reinforced nylon and aluminum. So there's definitely a spectrum there of what you can achieve, and it comes down to what you can do with design. Great. So I'm seeing a lot of just general questions about 3D printing carbon fiber, which is great. Why would you use chopped versus continuous? That's exactly what we're here to answer. So let's go forward. Let's first talk about the basics of carbon fiber. So what you think of as a carbon fiber, or what you think of as carbon fiber, has been kind of skewed by popular media. I think there's a specific type of kind of a sheen to it. There's a There's usually some sort of weave. You've seen all the like the car parts that are like it's a carbon fiber car part. A lot of those have stickers on them, right? It's a carbon fiber sticker. The weave is something that is definitely used in the aerospace industry and the automotive industry. But let's back that up a second and talk about what exactly carbon fibers are. So a carbon fiber is the result of a pyrolysis reaction. So it's essentially you're taking what we call precursor fiber, which think about like any like a long like a synthetic fiber. In the case of carbon fiber, we're actually using polyacrylonitrile, so a PAN, and that's being stretched out into very, very thin filament. And I'm going to make a note here on filament. In the carbon fiber manufacturing industry, filament denotes a very long, thin strand of substance. In 3D printing, filament is also a long, thin strand, but the scale is totally different, right? Like the filament here that we're talking about is 5 to 10 microns in diameter, whereas the filament that we're talking about 3D printing is, it's on the 1 to 3 millimeters in diameter. So it's like a totally different scale of material, 3 orders of magnitude different, but it's still a very long, thin filament. And the reason why there's all this hype around carbon fibers, if you look at it on that scale, even if it's this scale or blended with more fibers into a toe, these fibers are incredibly strong and stiff. Sorry, they're incredibly strong in tension, and that's where a lot of the root comes from. So what you get with carbon fiber in reality is like you take all these very long, thin 5 to 10 micron thick filaments, and we're blending those together into toes, somewhere on the order of thousands. You might see in carbon fiber manufacturing, you might say 1K toe, 6K toe, 24K toe. That's how many individual fibers there are. So you take a bundle of these fibers, put it together, and what you get is a toe, and that's the basic building block of the material. But that material on its own is just it's just yarn, right? That's what, if you see it in reality, it's like woven like a fabric. So because it's very strong in tension, when you combine it with with a thermoplastic material or a thermoset resin, it's gaining a lot more because now it's being held in place and the tension can be transitioned into flexural strength. So carbon fiber works best as part of a composite. And just like LeBron James is not going to take the whole team by himself to the NBA finals and win and score all the points, like he needs a team to help him. And carbon fiber, same way, needs some assistance in order to be the great that it is. So let's talk a little bit now after we've talked about the carbon fibers themselves. What is the 3D printing physics of like, well, what happens when you actually print it? So the practical implementations that I would say most common, and especially to Markforged, you see 2 types of implementations. There's a short fiber filled filament. So on the left, you'll see, hopefully you can see that those are the fibers that are actually used. There's no resin in this one. I will go through some photos later where there's included resin, but they're short, discrete fibers, right? You'll see a lot of people call out carbon fiber filaments, right? They'll sell on the market as carbon fiber filament. Most of you hopefully understand that those carbon fiber filaments are in fact composed of a lot of short carbon fibers blended into another plastic filament so that you can print it like your traditional FDM filament or FFF filament. Continuous fibers are a different story. And if you have worked with carbon fiber composites in the past or any sort of composites, fiberglass, be it that or anything else, the continuous fiber is where you're going to get a lot of this, like the real high performance strength. But it is, in the past, has been harder to form. And once you blend all those fibers into toes, there are a number of ways you can actually print them. You can use a thermoplastic, or you could use a thermoset. You can have a pre-pregged material, which means that is pre-impregnated with a resin, and that is then heated or cured with UV. So there are a number of different ways that it's implemented, but for the sake of our discussion today, we're going to go over the thermoplastic version, so using heat to melt and cool materials and set them into place, short versus long fibers. Cool. I'm going to take a minute here to play this video. So this is a video done by my good friend Alex Crease. He was previously at Markforged and put in made a lot of the great content that you're going to see on the website. This is a video that he put together with a sort of analogy on carbon fiber. If you have already seen this, feel free to take 2 or 3 minutes. Get some coffee, refill your coffee, send a text message, look at some memes. It's going to be about 3 minutes. If you haven't seen the video, I encourage you to watch.
Hi everyone, I'm Alex Crease here at Markforged, and today I'm going to be talking with you about the different methods of 3D printing composites like carbon fiber, fiberglass, and Kevlar. When people talk about composites in 3D printing, it can take 2 forms, chopped fiber or continuous fiber 3D printing. It all starts with a strand of fiber like this one. Fibers like carbon fiber are so valuable in engineering because of their strength to weight ratio, specifically when applied in tension. Alone, they sort of behave like raw spaghetti. You can easily break a piece of spaghetti by bending it, by compressing it, or by shearing it. But it takes a lot more force to break a strand of spaghetti in tension by pulling on it. And that's how fibers are most often used in composites. When you bond these fibers with a matrix material to help them take shape, they form incredibly lightweight, strong structures because the fibers can be laid out in these optimal patterns that make use of their tensile strength properties. So chopped fibers in 3D printing are a bit different, referring to small bits of carbon fiber broken up and mixed into a thermoplastic like ABS, PLA, or nylon. This gets extruded into a spool, which can then get 3D printed with a deposition-based printer, but doesn't leverage the continuous strength of those fibers. So it's sort of like a booster pack for standard 3D printing thermoplastics. It bumps up some of the material properties like heat resistance, strength, and stiffness, and may improve the print quality and dimensional stability as well. But the strength is largely defined by what's holding it all together, which is the thermoplastic. Continuous fiber printing is a variant of a deposition-based printing process called continuous fiber fabrication, or CFF. One nozzle builds a thermoplastic matrix material while continuous strands of fiber are ironed down into the part with a second. Software allows you to lay these fibers down in specific places with specific settings to optimize the part for its strength, just like with traditional composites. So a part reinforced with continuous fiber leverages the strength of the continuous strands themselves rather than relying on the thermoplastic for strength. And we can show what a difference that makes right here. So chopped fibers are basically a bunch of little pieces of a strong material adhered together in some way, like how these bricks are held together by their connection points. A continuous fiber takes that same material but forms a continuous connection across the loading surfaces of the same part, represented by these plates on the top and bottom. So when we apply a load to a chopped fiber part, it breaks at the connection points, which when applied to printing composites is just the thermoplastic holding it all together. When we apply this same load to a part with continuous segments spanning the load paths, in this case, the top and bottom plates of the part, the chopped segments act as a filler or a matrix material, and the load holds because it's being distributed across the loading surfaces by the continuous reinforcement. This concept is what makes the continuous fiber so much more powerful than chopped. I hope this clarified some of your questions about 3D printing composites. Happy printing.
Cool. Thanks for indulging me here. Sticking around. I took that time to read through some of the questions, and I hope I will be able to.
I'm Alex Crease here.
We'll go again. Okay. So hopefully I can answer a lot of these questions with the content, and I will definitely be going through in the next probably 5 minutes and answering these questions live. So let's talk a little bit about short fiber filled filaments. So I wanted to note again that all of the carbon fiber filaments on the market are going to use short or discontinuous fibers. Like if you're using an FDM machine, the material that's coming out is going to look something like this. It's not going to be the exact same blend of fibers. Maybe the lengths, the density is going to be different, but all the fibers are going to be on this order. So 5 to 10 microns in diameter. So we're taking taking these fibers and sort of chopping them up, chopping or milling to get them to size. And you're going to see them vary anywhere from 50 to 250 microns in length. Now, you might see some companies might make a specialty one that says like, oh, well, we use like very fine powdered carbon. Powdered carbon gives you some different characteristics. And then some might try to go for like even longer than 250. But for what I've seen in the market, 50 to 250 micron length is about right. If you go any longer, it gets harder to print. If you go any shorter, then you're just adding a kind of maybe a more conductive filler, not necessarily going to add so much to strength, maybe some bulk stiffness. As far as the filaments go, you'll see them be anywhere between 5 to 35% carbon fiber by weight. Again, you may see deviations from that. Like if you're going for a conductive filament, that tends to be it might even be on like a single digit scale there. But for the structural filaments, you'll see 5 to 35% by weight, and you'll have a pretty uniform distribution throughout. Like this is zoomed in very far here. You can see the scale in the corner there is 50 microns, but you're going to see this type of distribution all throughout the material. And the fiber is going to align with the direction of the print. The aspect ratio just sort of dictates that. Like when you're flowing this material in a continuously narrowing extrusion path, the aspect ratio of the fibers is going to cause it to align with the direction of the extrusion for the filament and with the printing direction, which is another type of extrusion. So zooming out a little bit, this hopefully shows you a bit more of that uniformity. There is a delicate balance between strength and flowability for these materials, and I'm only an armchair material scientist. I do what I can on Wikipedia and what's available, but essentially the benefits that you get from adding these chopped carbons or short strand carbon fibers is that there's a marginal increase in strength and stiffness. So some of you might see that it's actually like, oh, this is marginal, like it's a lot more than that. I say marginal as in like you might be able to double the strength, but chances are after the material's conditioned and you've used it for a while, it will be closer to an injection molded part in terms of strength and stiffness characteristics. So you're also going to get improved thermal stability. So this is where we're getting a kind of interesting benefits. Like these are the benefits that you're not really, people aren't really advertising. The thermal stability means that it's just going to print better. Instead of having like a coefficient of thermal expansion, which causes it to expand and then contract, you're actually going to see the material stay pretty stable as a bulk. So when you're printing it, you're not going to see as much warp so long as you've got your settings tuned in. And with Markforged, we obviously we take care of that tuning for you, so you don't have to do anything. But the stability plus the increased stiffness means that you also have better bulk part accuracy. So when we're talking about part accuracy, that involves the reduction of warp, like rigidity, so that it stays in place. Every single path of filament stays in place, and that results in better accuracy. But the challenges to some of this, you're also going to see that it is abrasive. So if you look on a Markforged machine, most of the components along the driveline now are made of hardened steel. That's because it is very abrasive. If you imagine the Mark I, my first nozzle on there had a brass nozzle for some of those materials. If we were to run Onyx through that, it would chew right through it. And if you have a hobbyist printer using brass material as the for the nozzle, you'll see that go. You might start at 0.4 millimeters as a nozzle diameter, but it's not going to be like that after a couple rolls. So I mentioned this earlier. Longer fibers or adding too much fiber can also negatively impact. Has a number of negative impacts. So it can impact surface finish, but it can also cause jams. And that's what we've seen with a lot of the fibers that exist on the market. In order to get higher strength numbers and compete with other filaments, you say, well, all the other filaments are saying that they have 60 megapascals flexural strength. Like we need to go higher than that. Let's fill it with more. Let's fill it with more. And what you end up getting is like just overfilling, which causes you just have a machine that can't ever finish a part because the material is always causing jams. So what does that actually translate to in terms of strength? Let's just take a quick look at the numbers here. You can see on the left here that that onyx material and some of these carbon fillers are adding a lot of stiffness to the material, and you're also increasing the strength of the material. But I want to note that this scale on the left here actually comes down and is that scale on the right. It's the continuous fibers are just like it's a world of difference. It's an order of magnitude of difference in strength and stiffness. And so that's where we'll kind of get into the bulk of material next. So we've reached halftime. This is halftime Q&A. I'm going to go through a lightning round of the questions. Looks like I have 59 open questions. Hopefully I can do these pretty quick. Let's see. Starting from 10:06. I'm sorry I dragged you along here for the last 20 minutes. Hopefully I can still answer your question. You want to learn how hard carbon fiber is versus aluminum. Material hardness is going to be a little bit different because it is actually based on it's based on nylon. So if you compress, if you were to put a Sharpie in if you were to run a Sharpie test on it, what you would see is that the material is as hard as a nylon. But if we're talking about like stiffness, hopefully I can address that question with continuous fibers next. Best applications you would not normally realize. For the chopped carbon ones, it's like a lot of like end plugs and stuff. Honestly, it's like, sorry, I have it's a lot of like end plugs and caps and fittings if you're using a chopped fiber. But when we're talking about like the continuous fibers, it's really like you got to start looking around at parts that are just kind of a pain. Like anytime you say, oh man, I don't really want to source that. It's made out of aluminum. You could potentially replace it with a printed component using a continuous fibers. So let's see, impact strength, and some comparisons to let's see, to traditional layups. I would say that the traditional layup is going to be stronger overall because it is it tends to have fiber alignment built into what you're doing. Now that's for a scale of part that is very large, right? Like I'd say that the layup process is not conducive to making very small components. Whereas with 3D printing, we can actually very finely direct where the fibers are going. But if you have a large bulk part, you're going to see that be a lot stiffer than a printed part in general, because you can also have finer control or easier control over the bulk uniformity across the material. For a sense of scale, this is the build plate on the X7. It is 13 by 10, and then if we were to build upwards, 8 this way. So 13 by 10 by 8. This is about the scale that I would say makes sense for these materials. Obviously we've had some customers that take multiple parts, kind of full size and put them together into an assembly. That if you're a systems integrator, I think if you're bolting a lot of stuff onto a plate, that's the way to do it rather than trying to print like a whole plate of stuff. The whole tray. You can add different components to it, bolt those down to an aluminum tray or steel tray, however you want to do it. Let's see. A lot of questions for why we should get going with chopped versus continuous. Let's see, most reasonable applications for CF as opposed to other filaments. Yeah, so let's see. Why don't we jump in here and talk about continuous fiber reinforced composites. So this is a bit of an approximation here, but I found this really great web graphic that was highlighting the mountains of the solar system. And I thought, you know, this is sort of like a materials. Actually, I'm kidding here. I went and sought this out. I figured there was probably a mountain taller than Everest, but what people are trying to represent as very strong carbon fiber materials, you know, they'll sort of like tag onto the carbon fiber the name, right? Like they'll tag onto the hype and say, oh, we use carbon fiber. It's 5 times stronger than steel. Your filament's not 5 times stronger than steel. No, neither is ours, right? Like, but if you were to look at continuous fibers, it's a different story. When we're comparing these materials, the continuous fiber is an order of magnitude stronger. And I did see a question about when you should use carbon fiber filaments versus these, and hopefully this gives you some indication. So if you're using other plastics and you need better toughness or better stiffness, the continuous fiber is where you're going to get a lot of that strength. So as a comparison, I saw a lot of questions about aluminum here. This is a 6061 aluminum bar on the right side, and then we have a printed bar on the left. They have the same cross-sectional area, dimensions are the same, but what you're able to do with the carbon fiber, I'm not saying this works for every part. You can obviously make this part the wrong way, put the fiber orientation like orthogonal to this, and you're not going to get any strength. But if you have it along that line, you're actually going to see it be a lot stiffer than aluminum because the material at its base is stiffer. So alignment definitely matters here. And what Markforged can do, at least automatically here, is route fiber along the perimeter of a part. I want to show you a little graphic here of what that actually looks like. So this is a part, right? It's made in onyx, and what is inside, hopefully you can start seeing this, is a reinforcement. We call it like a backbone of the part. And this material here is going to be 10 times stiffer than the base material. So we're putting that along the outside of the part. And if you've ever done any like beam bending theory, or maybe in like a statics class in the past, done any sort of analysis on composite materials, putting the strong material on the outer surface is the best way to get the best bang for your buck. So that's the reinforcement, right? And so when we realize that is what's filling up the part, you get a part as a whole, which is just a lot stronger than what it could have been if it were filled normally with a chopped fiber polymer. Internally, this is what you're going to see. So you can see this is a pretty rich graphic here. I'm not even sure if I'm allowed to share this, so please please bear with me here. I'm going to try to work through it. Each of these delineations on that side is supposed to be approximately how thick a layer is, and the printing direction is out of plan. So imagine that you took a cut along like a, let's see, you know, here's a part. We took a cut and we're looking inwards to it at the fibers themselves. This is what the fiber distribution looks like. And so it's like a fairly uniform distribution of and tightly packed fibers. So I wanted to make another clarification here, but comparing the short versus the long strand fibers. In a filled filament, the discontinuities between short fibers are what cause mechanical loads to transfer through the matrix polymer. And that essentially limits the boost that you would get in mechanical properties, right? Like if you imagine like all these short fibers kind of pushing, not against each other, but having to then push through a kind of soft material, it's like getting dampened each time you're transferring a load. So with the continuous fibers, you're seeing a lot less transfer through the matrix polymer. You're seeing the transfer happen from fiber to fiber. And that is really what's going to make it feel a lot stiffer as an end part. and also what is going to give it its elevated strength. So let's see. To put some more numbers to this, we could compare the tensile strength of materials here. So for one, you notice that I put a claimed number here. I want to note that the material strengths that people use are not always conditioned to ASTM D638. So ASTM D638 essentially specifies a certain size of sample, but then also humidity conditions. And what I'm talking about here is specifically carbon-filled nylons. So nylon has the characteristic in which it is hygroscopic, meaning that it absorbs moisture from the atmosphere. Now, this can be good and can be bad. It's good because the moisture actually toughens the material. It makes it more, it plasticizes it, makes it more plastic, which means it can absorb more impact, more energy before deforming. But that also means that it is going to be less stiff. So compared to an aluminum 6061, some people are claiming that they're nearly half the strength, right? There's the claim on their website, of course, says contains a carbon fiber, which is 5 times stronger than steel, but it's ultimately still a fraction of the strength of aluminum in terms of tensile strength. Now, we actually do list values that are conditioned. So after we've done some testing, I would say that most materials on the market will fall in that 60 range. Onyx is at 40, and that's because we actually choose to use less carbon fiber. Don't tell anyone, because we get the bulk of our strength from the continuous fiber, not from the chop fiber. So we're optimizing the blend of onyx to print accurately, and that's sort of maybe the secret sauce here. Now, once you start adding continuous reinforcement, it's a totally different ballgame, right? 20% means that on any 10 millimeter, on any 10 millimeter section, if there's 2 millimeters in XY, so I would say like 2 rings in 10 millimeter part, you're gonna see a boost in strength. And you start adding 40, 60. We're not going to ever get up to 100% carbon fiber fill. And that's where I just want to put out kind of a word of caution here. If you look at our material sheet, you might see that 800 megapascals is like a reasonable number for tensile strength. But in fact, like, unless you really are filling it all the way to the brim, like making that chain link that we have in that video, chances are you're going to see performance that is on somewhere between the 20 and 60 range, more likely on the 20 to 40 range. But because it is distributed to the outside of the part, you're still getting a ton of that strength, like in practical application. Let's see. And what that means for you as an end user is that you're moving from the concept modeling, prototyping stage, and maybe you're moving from the like functional or actually end use plastic replacement components, which I would say that any of the carbon fiber nylons on the market can replace plastic injection components to some degree. I would say that if you had a plastic injection molded carbon filled nylon, it would be way stronger than anything that could be printed. But if you're comparing to, let's say, just a base nylon, you will see comparable results. And when we start moving up the technical requirements list, what's required is that we actually get stiffer materials, stronger materials. And so then we're moving into functional testing, validation, work holding and alignment tools, bending and forming tools, a lot of service tools. If you have a replacement tool in the field, maybe some part that came from a vendor that no longer exists, a lot of those can be done. And then you start getting into low volume production and specialty parts that are designed for the process. So yeah, the sweet spot is in low to medium volume with moderately high loading requirements. And that's really kind of the sweet spot for Markforged. I'm going to take a pause here and then answer some more questions. let's see. I'm gonna go. I'm unfortunately gonna have to go in reverse order here from most recent. So uh, let's see. Lifespan of hardened nozzles versus brass. So versus stainless. This I don't actually have a great number. There are a number of YouTube personalities actually. I think Modbot, CNC Kitchen. They do some reviews on hobbyist machines. Like we obviously have our own proprietary equipment, but yeah, we use a hardened steel nozzle, and I would say that the lifetime is like just like carbon fiber. Continuous fiber is an order of magnitude stronger. The hardened nozzle is an order of magnitude more wear resistant than a brass nozzle. Cyclical loading. That's actually a great question. I think based on light cyclical loading, it depends on the duty too, right? So if you're going for very light duty, kind of like vibratory wiggle, like I would say that it's probably fine. If you start kind of doing like really big oscillations, that like in any carbon fiber composite could cause delamination. So that's something to consider is like the duty at which you're doing that. We also have different materials which are built. So carbon fiber is one material, but we also have materials which are built for that type of impact resistance. I would say our high temperature fiberglass is actually a great material. Kevlar, those are good at absorbing energy, and probably that would reduce the amount of deflection and delamination. Why is the Onyx ESD tensile strength higher than the regular Onyx? It contains a different type of carbon. So because it is a conductive, we're adding a conductive additive. That additive actually imparts more stiffness at the cost of some amount of durability. It also has a different polymer matrix, so there's a little bit of difference there. Reasonable maximum of fiber content without having issues. I'm going to jump back up to. I'm going to jump back up a few slides here. I think it depends on your geometry. Like I have to be fair here. I've seen parts that are loaded to about 60%, 70%. And that's because they were purpose-built designs optimized such that you could route continuous fiber all along. What that requires is some kind of a little bit of ingenuity. It's sort of like designing for a casting, in that you want uniform cross sections throughout, but you would just change the cross sectional width, section thickness such that you could fit more fibers through. We do have a design guide and also have a lot of content online about how to do this this design for additive manufacturing work. Let's see. Cost comparison: continuous carbon fiber versus Inconel. These are pretty different materials. I'd say the Inconel is probably more expensive. It's an expensive nickel alloy, but it's the characteristics are different, right? Like for us, our Inconel is not, our Inconel is a high temperature material. Our carbon fiber is not a high temperature material. We sit on the order of like 100 C to 150 C as like a safe maximum for operating temperature, whereas the Inconel can go up to like, I don't know, like over 1,000 C. Let's see. Dimensional tolerances. Can you machine the parts afterwards? I think we're looking on the order of like, for the desktop machines, 250 microns. We actually have a very specific guidance. The error scales with the size of the part. So at the low end, it's at 250 microns, and then as you're plus or minus, and then as you go up the scale, that's going to grow a little bit, on the order of like 0.2%. So after that, it's a little bigger. On the industrial machines, so the X7, which we talked about earlier, this size machine, it's got a laser calibration built in, as stiffer gantry. That can get you probably on the order of I think it's 150 microns, plus or minus, with a 0.1% grow after that. Hopefully that answers your question. Is it recyclable? Unfortunately, it is not. I would say that it's most of the parts that we see in use are not intended to be disposed. Like in that graph of applications, a lot of these parts stay in production, right? Like they're in production for 5, 10, 20 years. So while an aluminum component or a steel component could be recycled, a printed component would not be. But it is also significantly less material that you're using in a lot of cases, because you're not having to hog it out of a block. And all in all, I would say that the environmental impacts for this, and like we did a couple of sessions and crunched a lot of numbers. I would say that the environmental impact overall is still net positive because we're reducing the amount of material that's being shipped, we're reducing the amount of material which is being cut and disposed of, recycling, like reducing the number of times that material is being fired and recycled. So I hope that one day we can see a recyclable material. At the moment, it is not. Martin has a question. Is there actually a way to have CF filament certified as material for lifting and safety equipment? It's funny you ask that. It's almost like almost like this is like a placed question. One of our customers at Wärtsilä has built a CE certified lifting tool using printed components. You can find that the case study on our website. Look up Wärtsilä, Wartsila. Wärtsilä. They built a CE certified lifting tool for pistons, for ship pistons. So this tool is it's probably about this big. These components are each the max size of the X7, and so we've got 3 of them. It's a big tool, and this tool can lift close to 1,000 kilograms, which is it's a pretty impressive tool. My coworker Daniel designed it with the or helped design it with Wärtsilä, and it's really impressive what you can do. And the part itself weighs a fraction, right? It's a quarter of the weight. Let's see. Max volume, weight fraction. Volume and weight fraction is actually a little bit. So there are 2 terminologies here. I'll jump back up a few slides again. When I say that this is a continuous fiber reinforcement 60%, that is actually of our material, which of course has its own volume fraction. And so we don't really disclose what those are. But if you were to look at the strength of the material, you look at the data sheet, you could probably back out approximately how much fiber's in there. I'm not at liberty to disclose what our volume fractions are. As I said, with the chopped fibers, typically people order on somewhere between 5 and 35%. And for this material, because it is so much stiffer, I would say that it is higher than that. So how did you achieve 800 megapascals? And that is based on a pure printed beam. So if we're talking about like ASTM standard beams, we printed a pure fiber beam and measured based off of that. Like practically speaking, you'll never achieve that 800 megapascals with a printed part unless you were making a beam. But you could see somewhere close here, like you see 60%, you can get 500 megapascals. Is there any shrinkage after manufacturing? There actually is not very much shrinkage because it's a thermoplastic material. So the fiber keeps it from shrinking, which is pretty interesting. Yeah, hopefully that answers the question. There's no cure time for that one. Can the material be used on machines other than Markforged? I mean, if you can find it and put it on another machine, like I can't stop you. But officially speaking, no. We don't really sell it for other machines. Like it is tuned to work on ours, and so we wouldn't be able to take any liability on it if you were to take it and print it on another machine. Obviously, if you look at a lot of the academic research that's out there, they want specific type of pathing of materials that we just don't offer, because Eiger is made to be very simple and user friendly. We want to minimize the time that you spend going from art to part rather than spending a lot of time designing the part. So Eiger will not let you do a lot of that routing. So some people will buy our material and print it on other machines. Obviously, can't endorse that. You can machine parts after printing. Use a high-speed steel, so an uncoated cutter. I would say go at high feed Don't go too fast because then you'll heat the material up. So just be mindful that you can burn or warp the material. So lots of like little short like cut passes. That said, there is carbon fiber in the material, so just like be careful. If you're going to mill something, like be aware that there will be dust particles that come out of it. So make sure that you're using some cutting fluid that will then be able to carry that away without letting it go into the air. Let's see. Way to calculate final part strength for the design phase. I think the best thing that you can do here is take an estimate based on how thick your cross section is, and then I'll give you a rule of thumb. See if I have that slide here. Hopefully this can give you some clarity. So look up the composite design guide. That's available on our website. You might have to put your information in again to get it, but the fiber width is about 1 millimeter, right? So each pass of the fiber is about 1 millimeter. So when you're going into factor for the design of a part, imagine like each fiber path is 1 millimeter, and let's say for a 10 millimeter wide part, you get about 20%, right, for a single ring around. And you get 40% for 2 rings around, 60 for 3 rings around. So that can be used as a baseline for estimating, but unfortunately, we don't have any FEA tools yet. Tim, I see your question here that FEA data for continuous carbon fiber. We don't have it yet, but it's in progress. I think we're going to have some eventual API linking with. There was MSC, I think, is our first integrator that's going to build into our API and have an FEA format come out, but I would look forward to that sometime later in the year. It is not something that we can do right now, but if you wanted to just estimate based on 1 millimeter per path of fiber, I think that gets you pretty close. Let's see. Most presented data doesn't show variability in mechanical properties. How does the mechanical properties spread across samples compared between conventional and 3D printed process? Well, I'd say that we will have a dimensional accuracy report and also some more results. I think if you're looking at just the mechanical data, like I'm basing these numbers off of an average, right? And this is a conservative estimate of an average. And what you'll see, let's see if we can go back up to the data sheet number. Sorry to be jumping around here. Hopefully it's this one. Yeah. So the numbers are based on averages, right? So we can probably at some point release more data around what those samples look like. There is definitely variability, but it's yeah. I can't actually very accurately answer your question. I'm sorry about that. So Roy asked, did the pure fiber beam delaminate? Intention? No. For the tensile testing, we are simply just pulling that beam. In the bending test, I don't think the failure mode was delamination. The failure mode was still a clean break. What is the build rate? Build rate actually, Flores, if you wanted to go onto our website, go into Eiger, Eiger software will give you the estimated build time, and it's really accurate. Like if I'm printing a part and I want to put an insert in, like sometimes I'll pause a print, insert a magnet, insert like a captive nut. I can trust it to be within plus or minus like 5 minutes in that build rate. So go into Eiger and check that out. What applications? It's a nylon material, so you're going to need some coating if you want it to maintain rigidity. The good thing is the continuous fibers inside the part tend not to lose so much strength. So once you put the fiber in, and then you coat it with, say, a polyurethane or like an acrylic varnish, you should be okay for some wet application, at least for some time. Ease of adding internal metal components during the printing process. It's very easy. Eiger lets you pause the print at a specified layer, and then you can take the build plate off. Like This part actually finished, but if I had not finished, I would have taken it off, put it on my workbench over here, pressed in some nuts, and then started printing over. If it's a metal insert, nylon doesn't like to stick to metal, so I would first apply some glue to the top of that so that it can print over. But tends to be very easy to do. Let's see. We've got a lot of questions. Some of these I'm unfortunately going to have to get to a little later. I'm going to see. Resin being used generally with the resin that we're using is a nylon-based material. Others will use a variety of epoxies. We're using a nylon. 1 kilogram, 1.75 millimeter thick. Yeah, that's exactly what we're selling. But that's for the onyx material, granted. So the material here on the left, the continuous fiber is a different material. That is sold as a. Let me see if I actually have one here. Be right back. I do have one. So this fiber is a lot thinner, right, compared to the other one. And what you're going to see, I might as well stop sharing soon. But it's a different fiber, and this does not really print on other machines because we've specially built hardware, and this is also a patented technology by Markforged, so it's specific to us. Is there a lower limit to the radius of curvature for carbon fiber such that an attempt to turn doesn't weaken it significantly, even its matrix? We actually tend to do because we're using such a thin filament. Here's something to note compared to other 3D printers that are saying that they do carbon fiber. You're going to see this be able to turn in a lot tighter radius because it's pre-pregged. It's because it is continuous. Also, you could see breakage like at a very tight turn, but whenever we are doing those really tight turns, it tends to be because we're mimicking an isotropic pattern. So we're mimicking unidirectional per layer, stacking unidirectional layers on top of each other. So it will make a sharp turn at the end. As to whether that breaks there or not, I'd say if you are intentionally going around something, then it would be fine. If you are trying to just go there and back, it may break at the end. But for small curves, like I'd say you could reinforce a 3 millimeter hole, no problem, right? Like you could go around a 3 millimeter diameter hole and not have it break. I've certainly done that in the past. Wear resistance. So that's Carlos, that's a great question. Wear resistance is improved by short carbon fibers. So the long strand carbon fibers are within the part, right? So you're not going to see that be, let me back up some slides here. So the long fibers are within the part. The short fibers are on the outside, and those actually do improve wear properties. So that applies to all nylon carbon fiber materials. Wear it bears a lot of that load instead of it rubbing on the plastic. Although nylon on its own is already very wear resistant. So the combination of nylon and carbon fiber, very wear resistant, very impact resistant. Alfie, MF can run ESD materials. Yes, we do have an ESD material available on the X7. The surface resistance range is between 10 to the 5th and 10 to the 9th. And if you print it with the optimal settings, it can be 10 to the 5th to 10 to the 7th. As it's an anisotropic material, it should present data on different directions. Absolutely. So I would say that if you were to look at the material characteristics in the Z plane, you're going to see that behave just like the base plastic. It's not going to be, I won't make any claims about that. Like we are 2.5 dimensionally strong. We're good in compression in Z. We're good in XY. But if you were to pull on a part, which is, you're printing layer by layer, it's like pulling a phone book apart, right? you're not going to see the strength there. It's going to behave like plastic in that sense, because of the only strength that you're getting is the bonding between the layers. Material outdoors, chemical UV resistance. It's the nylon based material is already very good outdoors. The carbon fiber actually, the chopped carbon in the nylon reduces the UV exposure towards the inside of the part. And what that means is that you're going to hold up very well outside. Chemical, not good with acids and bases, but good with solvents. So any sort of like petrochemical solvent, like it's fine with that. Just acids and bases are nylon's kryptonite, or kryptonite is the acid for nylon. Anyways, possible to print a bike frame from carbon fiber, really small bike frame for us. There are some companies that are doing big resin-based carbon, like continuous fiber printing. You can probably check some of those out. I'd say if you're going to build a bike frame, you can print the joints, and we had a number of customers that do just that. You can also build tooling for welding fixtures and such. What binder to use for the fiber strand? It is still it's a nylon, so we're using the same material such that so it's thermoplastic nylon such that it can bond to the other material. If we were to use an incompatible polymer, then you would see delamination from the shell and the material and the fibers itself. So we use the same base nylon. Let's see. I see. Can the mini printer on my table? Yeah. So somebody's noticed in the background that I have a personal Prusa Mini. That I'd say if you really wanted to, you could. I would not expect my machine to last very long. Like I want to keep this machine. It's my personal use machine, right? So PLA is very very easy on it. I just like to have it run PLA. Maybe PTG, but not. I wouldn't run the Onyx on it unless I wanted it to have an early end to its career. Maybe with some like swapping of materials, or if I were okay with getting new print heads every once in a while, it would be fine. But like you need to upgrade the extruder hob, the nozzles, like then you have to find make sure that you have a source for all those. So I'd be cautious about that, but you certainly can. How many filaments have a toe of carbon fiber? So the toe of carbon fiber is specifically the carbon fiber reinforcement material. The Onyx material does not have a toe within it, right? So that is all chopped carbons, whereas the continuous fibers are all toes. So if you look at our materials, if you go to the Markforged webpage, you'll see composite base and continuous fibers. Continuous fibers are all continuous toes. Studies on fatigue life. We're working on those. We don't have any yet, Richard. Sorry about that. Porosity, could they be used for applications that require waterproof sealings? I would say that you would need to seal them because they're FDM. Like you are printing in discrete layers and discrete paths. In order to get that to seal, I'd say that you could use a sort of vacuum impregnation. That might be good, or you could use a spray coat if it's not so critical. Spray coat seems to work pretty well. Nylon can be recycled. Why not nylon CF? It's just that nobody wants to recycle a material that contains carbon fiber. Eventually, yes, I'd say like theoretically, there's no reason why you couldn't. But nylon as a polymer also does degrade with each recycling. So with nylon CF, like theoretically, you could take nylon CF, blend it up, make it into pellets, but you didn't have reduced uniformity. Eventually, I would love to see it recycled, or maybe if we didn't use nylon, we use another polymer. Parts legal to use on cars, boats, vehicle. I think a lot of the safety standards are going to be on a case-by-case basis. So you can use it however you want, but there's no like national highway safety guideline on it. Let's see. Continuous fiber in a compliant mechanism. I would actually probably recommend our HSHT fiberglass. So although it is intended for high temperature or high strength at high temperature, it is also a very rigid, like a robust material. For cyclical loading, you could use carbon fiber, but it is going to be a lot stiffer. So it depends what your use case is. I have seen use cases like internal use cases for compliant mechanisms. So like reach out to us and we can see about getting you a sample part or something. How do textures print in continuous fiber parts? Well, the texture is always going to be on the outer surface, right? That's going to be the discontinuous fibers. And it does look like we're a little over time here. I'm sorry if I did not get to your question. I know I front loaded a lot of these questions, and some of you, if you're still here, I'm very sorry that I didn't get to answer your questions live. But we will reach out and answer all your questions directly, and hopefully that gets you an answer. And if not, you know where to find us. Let's see. Support after purchase. Support. That's a great question. Support happens. Like we have a whole support team. It happens in two ways. So we have an internal support team. So if you have problems with the software, problems with materials, like the hardware, you can send a ticket to us, and we get you in touch directly with whoever is closest to you. So we have our internal team, but then we also have a network of partners around the world. And chances are, if you bought a machine, you would get that from a partner, and that partner would come in and install it for you. And anytime you need service, you can call them up directly. You can send us a ticket, and we'll route it back to them. So phone support is available. We tend to, I do think that our support portal is quite handy. And rather than waiting for somebody on the phone, it is often faster to either call the reseller or the partner reseller who can come out and do that service for you, or you can reach out to support or kind of DIY. For the most part, I don't really personally even have many issues. Like most of the stuff is like, oh, I need to order this replacement component. Okay, I'll go online, order it, and then I'll replace it that way. Let's see. Alvin says, I would like to print exhaust shields. Would continuous or chops be best for HSHT? For an exhaust shield, I'd say if it's not under like any directional loading, the chops might be okay. HSHT reinforcement will get you higher temperature. So see what that at the exhaust shield. Yes. See what the temperatures are like in that area. We have heat deflection temperatures listed in the material spec sheet. So if it goes above that, then you might be out of luck. If it's within that range, you're okay. Another option, if you wanted to make an exhaust shield, is to actually print tooling. So you could just form sheet metal if you wanted to. That seems to be something that's been quite popular these days that I've seen. Custom sheet metal, if you can get it cut to size, order a cut sheet and then press it with custom tooling, that seems to work pretty well. Application for 3D printed carbon fiber into metal. That's Rafael. That's exactly that is. We're on the same page here. Is it stiff enough to be used in a die and tools? Yes, we have a number of case studies actually on our website about use in sheet metal forming operations. So hopefully that answers your question. It can be done, and the continuous fiber helps a lot. Your surface is still going to be that chopped material. So depending on how many shots you're trying to go for, you may see that is not going to last as long as a tool steel die, but you can certainly use it in shaping. Yeah, I would not use it in any shearing operation. Pulling layers part with fiber weaker than pure onyx. Roy's question here. That's a great question. Logically, I think so. It's not like significantly weaker, but it probably is weaker. The onyx being that it's just more polymer bonding to more polymer. Fibers don't bond to fibers, right? So if you have a material which is more fiber trying to bond with another material with more fiber, you're going to see probably the polymer bond being stronger. Print molds for carbon fiber sheet. Yeah, absolutely. You can definitely do that. You are limited by size, unfortunately, right now. Adhesion issues with that. You would probably have to do a surface treatment. So whatever mold release agent you use for a traditional process, use that. I would recommend smoothing the surface too. And there's something actually coming out soon with us. We have been working with some post-processing companies, and there's some really interesting developments on what you can do with printed parts. Maybe that will be the next thing that I present, maybe next month. But surface preparation for molding operations and end-use components is a pretty hot topic. Alberto, best way to test is the trial. You know, rather than printing it yourself, even just get in touch with us. We have a network of resellers worldwide, and they can provide you a sample part. They'll print it on their machine, right? No need to tear up your machine. Just like I'm not going to print Onyx on my Prusa Mini over here. I would not recommend you print on your Maker Gear M2 either, mostly because I just wouldn't want to see your machine get torn to pieces by the carbon fibers. But you know, you do it once or twice, it's probably okay. I will say that the process of printing our material on another machine is not going to be easy. We spend a lot of time tuning this stuff, right? So to get it to stick, just the bed adhesion is a question on its own. To extrude and retract properly, there's so much that goes into that. And I work with some of our materials engineers that do this fine tuning. And yeah, I'd say it's just not worth it on a machine like this, especially if I do the tuning and then the components wear out. I can't source the same thing. Then my recheck rates change. It's like this whole nightmare, which can be pretty easily avoided just by getting the stock hardware. What type of carbon fiber is used? We're using the carbon fiber from probably the pan process. I actually don't know exactly. It's outside of my pay grade to know what exactly the carbon is, but we are using short strand carbon, obviously, in the Onyx, and long strand carbon. The count is going to be like, I don't actually know what the K count is for this, and yeah, it should all be pan based carbon fiber. Yeah, hopefully that answers the question. But you know, don't take my word for it. I haven't actually been told what it is. Difference in composition between Onyx and Onyx FR. Different. I think the fiber fraction is pretty similar. We just added an anti-burning additive, or rather a additive which undergoes an exothermic reaction and stops burning. That's what it is. Why the Young's module is different? It could be because of the additive. It also has a different base polymer. So the fibers are the same. It's a different base polymer. So they're nylons, just different types of nylons. Rob says, can you print parts in contact with gasoline or oil? Yes, you sure can. Nylon is very resistant to petrochemicals, so that's totally fine. Hand calculation for stress, continuous fiber in the XY direction based on the number of walls and total height. Yeah, absolutely. Hopefully that estimate I gave you earlier, 1 millimeter per pass of fiber. So in any feature, let me see if I can go back to the slide here. For any of you who are still here, it looks like there's still 260 people on. The Mark II is currently on promo. So I just jumped to the wrong slide and happened. I realized that I forgot to even get to this slide. It's 15% off until the end of the month, I think. And I've been at Markforged for 4 years. We've never done discounts. So this is it's pretty exciting if you're interested in a Mark II. Actually, I have a build plate here under my desk. Well, I have a whole Mark II under my desk here. This is the size of the build plate. It's 12 by 5 by 6. Let's see. This way. Sorry, I was getting to something here. Yeah, so a feature is open feature, 1 millimeter per pass. So you're actually getting 2 millimeters. And the walls are about 0.4. So if you go into Eiger and take a look, it's free to use and get in there and look at the internal view and stuff. Each of the fiber passes is 1 millimeter, and then each of the material pass is about 0.4. So you can sort of calculate that way. Ignore infill and just take into account onyx. And yeah, I would say just count the infill as air. If you really wanted to count it, you have a thicker section, take what the volume percentage is. Like we actually list what the percentage is and multiply the strength by that fraction. But what I've realized in doing some of these calculations is that the onyx barely contributes to the base strength once you start adding fiber, because this fiber is just so much stiffer and stronger that like the onyx like hardly adds anything to the calculation. Let's see. David says our group is currently researching data interfaces. That's great. We too are doing some of that. We don't have any commands right now that we can use specifically, but we will be releasing. I think there may be more details on MSC's website than on ours, but we have something in the works with MSC around like an integration. So for FEA. So hopefully that I can answer your question. Let's see. Yeah, we're 15 minutes over. Still have 250 people here. So I hope I can keep answering questions. I do need to hop off in the next 5 minutes. Do you need to dry the nylon before printing? An honest attendee asks. You do not. Our material actually, I wish I could just have a camera that I can move around and show you what's in my office space. Well, not everything. But our material comes sealed with like pre-dried and sealed in an aluminized bag. So you just load it into a dry box, which you keep the deskin in, and you print out of the dry box. So you don't need to pre-dry your material. Now, if you leave your material in open air for a day or even like 8 hours, then you're gonna have some issues. So just my advice would be to load it quickly into the dry box and then don't touch it again. Good thing is with onyx, you don't really have that many options because you're either printing onyx or another onyx. So for me, I just tend to run the spools all the way out. And you don't need to dry it before. Let's see. Thanks everyone for joining today. I'm sorry if I didn't get to your questions. I think I might have been overzealous in asking for questions, but we will get to them. We will get to answer your questions via email. We have your contact information, and we'll follow up with some of those. Mariel, thanks for putting this together. Thanks for putting me up to this. I hope this is informative for everyone. Please feel free to share feedback with us. If you want to type your feedback in here, we'll see it here too. Or you can email us directly. This was great fun for me. I love talking shop about carbon fiber and about use cases. So hope that we can reconnect again for the next webinar. Thanks for coming.